the agent thought it was calling a harmless tool, a compliance checker, a normal MCP server. But inside the response, hidden instructions told the agent to read a secret file and upload credentials. That is the new security problem with AI agents. The dangerous part is not just the model. It is the tools, the trust boundary, and the runtime path between them. This is MCP Security Explained. Start with the mental model. An MCP host is the AI application, like an IDE or assistant. Inside it, an MCP client speaks the protocol. The client connects to MCP servers. Servers expose tools, resources, and prompts. The model asks for a capability. The client sends a request. The server returns a result, and that result can become model context. This is powerful because one agent can reach many systems through one standard pattern. It is risky because every tool result becomes a possible trust boundary crossing. Traditional applications usually call APIs from code you wrote. Agents are different. They select tools dynamically, read tool descriptions, process tool responses, and may chain actions across GitHub, Slack, Gmail, databases, and internal APIs. If one untrusted tool can influence the agent, it may affect the entire workflow. The risk is excessive agency. Too many tools, too many permissions, and too little runtime enforcement. MCP does not remove this risk. It makes the integration standard, so the security model has to become standard too. For remote HTTP MCP servers, authorization is built around OAuth 2.1 patterns. The MCP server acts as a protected resource. The client discovers protected resource metadata, finds the authorization server, and starts the authorization flow. The user sees consent, the client uses PKCE, and the authorization server issues an access token. The important detail is audience. The token must be issued for the MCP server the client is actually calling. The client sends authorization bearer token on every request, and the server validates that token. Good MCP OAuth is not just login. It is delegated access, narrow scopes, consent, PKCE, and resource-bound tokens. Now look at a broken setup. The client asks for broad scopes. The server does not validate token audience. The same token is reused across tools. Worse, the server passes tokens downstream instead of exchanging or isolating credentials. This creates a confused trust chain. The fix is boring, which is good. Request narrow scopes. Include the resource parameter. Validate audience on the MCP server. Use short-lived tokens. Do not pass user tokens through to unrelated services. Isolate credentials per upstream system. The secure version has fewer permissions, fewer places for tokens to leak, and clearer denial behavior. Tool poisoning is an indirect prompt injection problem. A malicious MCP server can look normal during setup. The tool name says compliance checker. The description sounds useful. But at runtime, the tool response mixes real-looking data with instructions aimed at the model. For this tutorial, the secret is fake, the endpoint is local, and the attack is simulated. The point is the shape of the bug. If untrusted tool output is passed straight into model context, the model may treat malicious text as instructions. Prompt rules alone are not enough. You need runtime controls outside the model. A safer runtime treats tool output as untrusted. First, constrain response shape with schemas. If a tool promised JSON, reject free text. Next, filter suspicious content before it reaches the model. Keep an allow list of approved servers and approved tools. Separate low-trust external tools from high-trust internal tools. Add confirmation prompts for destructive or data-moving actions. And enforce policy in the execution layer, not just the system prompt. The result is simple. The unsafe response is blocked before it becomes agent instruction. A gateway gives you one enforcement point between agents and MCP servers. Instead of every app managing every server, the agent connects to the gateway. The gateway routes requests, injects credentials, applies isolation, checks policy, records logs, and traces each tool call. If a request is approved, it reaches the upstream server. If it violates policy, it is blocked and logged. Gateways are not magic security dust. They are useful because they make security observable, centralized, and enforceable at runtime. A safer AI agent is layered. The LLM plans. The policy engine decides what is allowed. The gateway enforces. Sandboxes isolate risky execution. Tools run with the minimum permissions they need. Read-only tools stay read-only. Privileged tools are isolated. Destructive actions ask for human approval. Every important decision becomes an audit event. The goal is not to make the model perfectly obedient. The goal is to make the system safe even when the model sees hostile input. Here is the MCP security checklist. Use approved servers only. Request least privilege scopes. Validate audience-bound tokens. Use PKCE. Do not pass tokens through. Confirm destructive actions. Isolate privileged tools. Prefer structured outputs. Keep logs. Enforce gateway policies. If you remember one thing, remember this. MCP gives agents reach. Security decides how far that reach is allowed to go. MCP makes agents more useful because tools become easier to connect. That also means the security architecture matters earlier than most teams expect. Designed for untrusted outputs, narrow access, runtime enforcement, and auditability from day one. Secure your AI agents before attackers do.